Everyone come. FIFA give us a new ball. You want to know if it's any good? And we're here to help.
I'm Adrian.
Hi, I'm Derek. And, FIFA actually puts a lot of restrictions on the nature of the ball. They tell us how big it needs to be, its weight, how round it has to be, even how it takes on water. But there are no restrictions on the surface quality of the ball. It could be rough, it could be smooth, and that really affects the way the ball moves through the air. So what we want to do in this video is help you understand what the next ball is going to do once you see it.
The key surface properties that the ball manufacturers can change are the texture of the panels, the total seam length, and the total seam depth. Of these three things, the two most important for the aerodynamics of the ball is the total seam length and total seam depth. The longer the seams and the deeper the seams, the rougher the ball.
Yeah, you might think that, these tiny little seams on the ball don't amount to much. Well, it turns out that the depth of that groove is exactly at the right scale to change the manner in which air flows around the ball. It has a huge effect.
There are two types of flows around the ball: laminar flow and turbulent flow.
Okay, so let's take a look at these graphics showing a soccer ball moving at high speed and a soccer ball moving at low speed. In both of these plots, we're showing the boundary layer here by this dark blue region next to the ball. That's where all of the interesting physics is going to take place.
And you can see, in the case of high-speed turbulent flow, the turbulence in the boundary layer is depicted by these black squiggly lines. This turbulence in the boundary layer means that the boundary layer hugs the ball very tightly and the boundary layer separates late. This means that the wake is small and consequently there's low drag. On the other hand, in the low-speed laminar regime, the boundary layer separates earlier from the ball compared to the turbulent regime. This means that there is a large wake and consequently high drag.
Okay, so let's take a look at how a spinning soccer ball can bend. So in this graphic, we've got the boundary layer flowing along this direction as the ball moves from right to left. The ball is also spinning. Now, this boundary layer is actually a low pressure region. You can understand that as the particles stretch out around the arc of the ball. And it turns out that there's an additional effect when you have a spinning soccer ball, and that on the side where the motion of the ball is in the same direction as the motion of the boundary layer flow, those two work together to create an extra low pressure regime, pressure that's a little bit lower on this side compared to this side. But that's not the only effect.
Because the boundary layer particles are more spread out on this side of the ball as compared to this side of the ball, the boundary layer separates later on this side relative to this side. This creates an asymmetric wake and consequently pushes the ball in this direction, allowing it to swerve.
Yeah, you've got a longer arc of the ball here that has low pressure boundary layer flow next to it, and that low pressure pulls the ball on this side to create a strong side force. Now, if you think about it, if you want a ball to bend well, you need a smooth ball. A smooth ball is going to make sure that this boundary layer isn't spoiled, but rather it stays right next to the ball. A smooth ball will have a low pressure region right next to it, and it will bend much better than a rough ball.
Using this knowledge, we can solve differential equations that enable us to plot the trajectory of different balls. In this image, we show the trajectories of different balls from a typical free kick position. The yellow trajectory over here depicts the path of a ball if there was no aerodynamics switched on in the case of no air. These 4 balls show the trajectory of the Brazuca, the 32 panel ball, the Jabulani and the Team Kite. You can see that the rough Brazuca bends less than the smooth Team Kite. The Jabulani is also a very smooth ball and it bends almost as much as the Team Kite, whereas a 32 panel ball bends very similarly to the Brazuca because it has similar surface roughness properties. And when we look at the Jabulani, it really is smoother than other balls. The 2 most important things, the seam depth and seam length, mean that it's smoother. The total seam length is shorter and the seam depth is shallower.
Yeah, this ball caused a lot of trouble. And Adidas didn't want to get the same thing twice, so they really made up for it with the Brazuca. This is an incredibly rough ball. It's got a very long seam length. It snakes all over the ball and it's really deep. And not only that, they put a really rough texture over the entire panels. So this is a rough ball and probably one of the roughest we've seen. I mean, compare this roughness with the Team Geist.
Have a look at this ball. The Team Geist is a very smooth ball. Even the panels are very smooth. This means that the boundary layer stays intact longer as the ball slows, meaning it will bend like crazy.
So look at the variation in these balls over the years.
The 32 panel ball of early World Cups, 2006, the Team Geist, 2010, the Jabulani, the Brazuca in 2014, and the 2018 Telstar 18.
And now you're ready to get serious about learning how the next World Cup ball is going to play. If you're interested in these sorts of things, there are additional images in our paper, and you can access our paper just by having a look at the details below.